This video is for chapter 14 and it's on the Arrhenius equation. You should make sure that you have read this section in your textbook and understand who Svante Arrhenius was and read about the equation itself. But this is going to give you a brief overview of what you need to know. You should make sure you take notes in your packet as we go along. So the Arrhenius equation was derived by Svante Arrhenius to state and help us calculate a relationship between the rate constant K and the absolute temperature that the reaction takes place at. And remember, absolute temperature always implies that we're using the absolute scale value, so the Kelvin value. So in these problems, your temperatures would need to be in kelvins. Now, we already know that in order for a reaction to happen, there's a few factors that we have to consider. And we need to know that we have to have enough collisions per time. So, you know, the more collisions, the more reactions likely to occur. So the number of collisions per time affects our success rate for reactions. The number of collisions that occur with the correct orientation also is a factor. And then lastly, the fraction of those molecules that collide with the right orientation that have the energy that is at least equal to, if not greater than, the activation energy. And you remember that the activation energy is the minimum amount of energy needed to cause a reaction to happen. Now, when we consider all of these factors, Svante Arrhenius was able to put them into an equation, and the equation is in your note packet. It says K, the rate constant K, equals A, and then E to the power of negative E sub A over RT. Now this E right here, the little e, is a mathematical function. You're using the button, if you looked at your natural log button on your calculator, above it should say e to the x. So that's the function you're using there. It's an exponential function. So these are the different factors or variables that are in this equation. K is your rate constant, and the units of K will vary, because we know that for a zero-order reaction versus a first-order reaction versus a second-order reaction, you'll have different units on K. A is a frequency factor. It tells us how many collisions there are in the orientation of the molecules. E is your activation energy. R is your ideal gas constant. And although last year you learned a bunch of different values depending on units, for this type of problem, this is the number you are going to use, 8.314 joules per mole Kelvin, and this number is in your data booklet. And then lastly, the temperature has to be in kelvins. Now, E sub A, so the activation energy, and that frequency factor A are experimentally determined, and they're specific to a reaction. So for every reaction you do, you'll have different EA and A values. They're not numbers you're going to memorize. Now, the Arrhenius equation, if you look at this equation here, this is an exponential equation. So if we graphed it, we would get an exponential curve versus a straight line. So we can linearize this equation by putting it in y equals mx plus b form. Now somebody else can do that. We don't have to worry about how that happened. But this is the form of the equation that's useful. And when it's like this, now it's in y equals mx plus b format, where y is the natural log of k. Your m, your slope, is negative e sub a divided by r. Your x value is 1 over t, and remember t is in kelvins. And the b value is the natural log of the frequency factor a. All right? Now, chances are the first thing I should probably tell you is that you all will have to do this on your chapter 14 exam. Every one of you will have to do an Arrhenius equation problem. But only those of you taking the higher level exam in May will be doing this on the actual IB exam. Now, none of these problems are very difficult, because if you know how to solve for, you can do y equals mx plus b, you can do these problems. So below, you'll see that we have 2 practice problems. I'm going to work through the first one with you in the video, and then I'm going to let you try the second one on your own. So if you look at the problem, it says use the following data to calculate a value for the activation energy for the reaction. Okay? Now I'm going to step back to the last slide for a second. And I'm going to go back to this problem. If you look at the equation in y equals mx plus b form, m is equal to negative e sub a divided by r. And in our problems that you're going to be finding, you're going to be wanting to find the activation energy. So if you do a little bit of algebra, you're going to figure out very quickly that negative r times m is equal to e sub a. What that means is, if you can find the slope of the line, you always know what r is 8.314, you can then find e sub a. And to find slope, you guys might remember from algebra that you pick 2 points on the line. The change in y divided by the change in x, or in other words, y2 minus y1 divided by x2 minus x1. So, going back to our practice problem, the data that I gave you, 1 over t represents our x values, and natural log of k represents our y values. And you can count any of these points along the way. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 different data points. And since I want you to find the activation energy, we know that activation energy is equal to the opposite of r times the slope. Now, since I know x and y, I can find the slope by taking y2 minus y1 divided by x2 minus x1. Now, to take your points, to do the best value of this, I would take the smallest and the highest values, because you're going to get the best average when you take the farthest apart. Okay, so I'm going to use y value. Y2, I'm going to say is 10.7, and then y1 is 2.27. Now, you'll notice that there are no units on natural log of k. There's a reason for that, but it's a little bit complicated, so just trust that there are no units on the natural log of k. Then we're going to divide it by x2. So we're going to take this first value, 0.00125, that's our 0.2, and then we're going to subtract from it 0.00250. Now you want to be careful a little bit along the way with your significant digits. Remember, when we're subtracting, we're counting our decimal points. Since 10.7 only has one decimal point, we can keep 8.4, no units. This one, each value has 5 decimal points, so we can keep 5 decimal points in our answer, and we're going to get negative 0.00125. And that label, if we were careful here, is k to the minus 1, which is the same as 1 over k, k being Kelvin. Now when you do this math, you get a negative 6.7 times 10 to the third, and that should be in kelvins. Keep in mind, we're going to divide 1 by 1 over k. 1 divided by 1 over k is the same as multiplying by the reciprocal k over 1. So the answer that we get for our slope is in kelvins. Now, we're not quite done with the problem because we need to find E sub a. But we know that E sub a is equal to the opposite value of r times the slope. Now we know that for r, we're going to have to use 8.314, and that is in joules per mole Kelvin. And we're going to multiply it by our slope that we just found of negative 6.7 times 10 to the third kelvins. Now you can do the math in your calculators. You can look at your labels. Kelvins are going to drop out. And so we should have a final answer here for this problem of positive 5.6 times 10 to the fourth, and that would be joules per mole. And you used data from a straight line to find the slope of the straight line in order to find E sub a. That's how we'll be doing these Arrhenius equation problems. So if you go to the next problem, this is the problem I want you to try on your own. Now I'm going to point out that I'm still asking you to find activation energy, but please, please, please be careful. Notice the labels here. I'm asking you, I'm not giving you 1 over T this time, I'm giving you temperature. And I'm not giving you the natural log of K, I'm giving you K. So you're gonna have to do something to this data first, and then do the process we just did. So if you wanna try this, I would pause the video right now, I would work through the problem, get an answer, and when you're done, you can turn the video back on and check your answer. The answer that I have for this problem is 8.98 times 10 to the 4th joules per mole. And that is the E sub A that you should get for this second problem. So hopefully you understand how to use the Arrhenius equation now. And if you have questions, make sure you jot down your questions so that you can bring them to class and we can talk about them on the next class period.